This session is by Professor Dr. Krishna Giri, Associate Professor, Department of Mechanical Engineering, Indian Institute of Technology and Palakkad. Professor Dr. Krishna Giri has research area in the area of combustion and laser diagnostics, in combustion modeling, novel laser and optical diagnostic techniques. He has several publications on flame stabilization, diffusion flames, counterflow diffusion flames, turbulent diffusion flames. And we are, on behalf of Department of Mechanical Engineering, College of Engineering, Muttatara, I extend a hearty welcome to Professor Dr. Krishna Giri and pass on to the session to Krishna Giri, sir. Sir?
Yeah, good evening. Can you see me?
Yes, sir. Yeah.
Yeah. I hope you can hear me well as well. Let me also share my screen. Just give me a minute. Can you confirm if you can see my slides?
Yes, sir. It's visible.
Yeah. So, good evening, everyone, and I'm happy that this FDP on green energy solutions, building a sustainable carbon neutral world, is being organized by the Mechanical Engineering Department of College of Engineering, Muttatara. So if you have any questions, you may even stop me during the talk and ask. Right. So I would like to start off by talking about hydrogen. A lot of you are familiar with this word elixir. Elixir, I mean, water is called as the elixir of life, and is hydrogen in some sense the elixir that we are all looking for? Because it seems to be the buzzword, and it is seen as something that can solve all our issues, all the troubles in the world in some sense. So what is hydrogen? Hydrogen is a gaseous element. In bimolecular form, it is hydrogen molecule. It is present very ubiquitously in nature in the form of gaseous hydrogen, but it is also present in the form of or as a constituent in various compounds across the Earth. Not just on Earth, but also on other celestial bodies like the Sun and various planets as well. So hydrogen is very, very common in nature, in organic life forms, and in the form of water, which consists of 2 hydrogen atoms and 1 oxygen atom. So it is present, but then again, it is not present in the form that we can easily use it. Okay? It has utility in many applications. Hydrogen is used as very commonly as a fuel. It is again found in various chemical compounds which have applications. It is used in fertilizers. It is there in every organic life form, and so on. But as a fuel, it is much sought after because it has an extremely high calorific value based on mass. So if you compare it with a typical hydrocarbon fuel, this has about 3 times the calorific value, but that's based on mass. Hydrogen, on the other hand, is a very poor fuel in terms of the energy content per unit volume. That is because hydrogen is a very low density gas. It needs to be stored at very high pressures and low temperatures for you to store more of it. Right. So in 1 meter cube, you will be able to store extremely small mass of hydrogen as compared to even a gaseous fuel like natural gas, or let's say a liquid fuel like petrol or diesel, which has about 10 power 4 or 5 times the density of hydrogen. It's an excellent reducing agent. Of course, all fuels are reducing agents in the sense they get oxidized and release energy. which is the in either thermal form or directly as electrons, which is what is utilized in a fuel cell. It is extremely flammable, which is a problem when you are looking at how you can store hydrogen. It can easily catch fire. It is seen as an explosive fuel. But on the other hand, the flammability of hydrogen is advantageous also, because you can use it very easily as a fuel in practical devices. You do not have to design or you do not have to worry too much about designing your combustion device. It has a very wide flammability regime, even with very little oxidizer, which most commonly the oxidizer is air. Very small percentage of air, you can have hydrogen combusting, which is advantageous, but it is also disadvantageous when you look at the explosive nature of the of hydrogen. So what is the problem then? I mean, why are we even thinking of hydrogen as a fuel? So if you look at the graphic on the left, you can see that the greenhouse gas emissions by various sectors is shown here. For instance, if you look at energy that's used in industry, it contributes to about 25% of the total greenhouse gas emissions. Energy use in various buildings, such as the electric power that you use in buildings, or it could be, let's say, for cooking and other purposes, that contributes to about 18%. Transportation, which is a major contributor to greenhouse gas emissions, is about 14.3%. 27.1% is under miscellaneous uses such as agriculture, forestry, land use, chemicals, and cement industries. Then there is the energy use in agriculture and fishing. Again, this is pertaining to the use of agricultural implements like tractors and so on. Those do not come under transportation. Then there is some emission from the energy production, which is also quite significant. And then there is some other fuel combustion, which is neither for industry nor for agricultural purposes or for domestic purposes. So that contributes to about 6.9%. So we essentially have, out of the 25%, 6.1% is for energy related, mainly for iron and steel industry. So power production and other uses contribute to, let's say, about 19%. So what this means is that irrespective of what the application is, greenhouse gas emissions are a major component of your, or rather, greenhouse gas emissions is very, very common. That is because about 85% of our energy needs are satisfied by combustion-based energy solutions. So even though we can talk about solar power, wind, hydro, and whatever, across the globe, much of our energy needs, it may be cooking, it may be energy production in a coal power plant or a diesel power plant, it could be through, let's say, biomass based energy solutions. All of these contribute to about 85%. And so combustion is a very important source for producing energy. So which means that combustion is not going away, but we want to reduce the greenhouse gas emissions. This is only possible if you replace hydrocarbon fuels with hydrogen as a fuel, because it does not contain any carbon. Okay. So if you look at the global hydrogen consumption by industry at present, we'll see that much of it is used in petroleum refining for various processes, which is like a value addition for petroleum industry. Then you can use it for methanol production, which contributes to 10%. You have ammonia production, which contributes to a major this thing. Ammonia is a fertilizer, and it is also a precursor for urea production and so on. So as you can see, majority of the hydrogen that is being produced, irrespective of what the source may be, it's used in ammonia production. And then you have certain other this thing like petroleum refining, which is major. And then among some 10%, transportation is also one of the uses. Okay. Now, if you look at this total 100%, that is still not even 1 to 2% of the energy needs that are satisfied through hydrogen across the globe. Okay, which means there is still a significant proportion of solar energy, wind energy, but hydrogen as a fuel or as a solution for energy production is not a viable option yet. Okay, so why are we looking at this? Because carbon neutral fuels are essentially, or carbon neutral solutions are those where the carbon emitted in the form of either carbon dioxide or as carbon fixed into the soil is essentially balanced by the carbon that is removed by the trees that we plant. And then this leads to the net zero emissions, meaning that whatever emissions you are generating will all go back to the organic life forms, namely, primarily trees. Okay. Carbon negative is where you remove more carbon from the atmosphere than what you emit through your industries or through power production technologies. We want to move towards net zero initially and then to carbon negative so that the global warming can be reduced. So for that, hydrogen is the way to go in a major way. And as you can see, even wind energy is sort of rooting for hydrogen in this fight between hydrogen and carbon dioxide. Okay. So carbon-based or fossil-based fuels mainly are a major problem because they contribute to the greenhouse gas emissions, and hydrogen or hydrogen carriers do not contain carbon, and that is a viable option as far as the reduction in greenhouse gas emissions is concerned. So why hydrogen? It can be used in various applications. It can be used for upgrading biofuels. It can be used majorly in metal and steel production. It can be used in transportation industries. It can be used as a source for power plants, for power generation. It can be used in an electric grid as a sort of as an additional source of energy to sort of what you could call as bolster the grid, or to make the grid more robust. It can be used in chemical industries. It can be used for domestic and commercial heating infrastructure. Pharmaceuticals is a major application of hydrogen as a source, right? And then various synthetic oils and fuels can be produced. Sustainable aviation fuel can be produced from hydrogen, and it of course already finds a lot of use in refinery. So hydrogen's uses are growing, which means that if you want to replace your conventional sources like fossil fuels in any of these applications, you will need to produce hydrogen at a much higher rate. So any talk that you would have attended till now on green hydrogen, you would have come across these colors of hydrogen. I personally do not agree with many of the categorization that's given here, but this is quite widely accepted as the categorization, which can essentially tell you what is the way to go. So if you look at the green hydrogen, which essentially means hydrogen which is not polluting, that is the hydrogen that is obtained from the electrolysis of water. And this electrolysis obviously requires some energy input. You supply some electric power to split the water molecule to hydrogen and oxygen. During this process, if the electric power that is input is obtained from renewable sources, then the hydrogen is termed as green hydrogen. On the other hand, let's say the energy for the electrolysis is not obtained from renewable sources, then let's say it is obtained from nuclear sources, then it is called as pink hydrogen, and there are other categorizations also. The most common way of producing hydrogen at present is from natural gas through steam reformation. If that includes some carbon capture and storage. So as you know, natural gas is nothing but methane, which contains 1 atom of carbon and 4 atoms of hydrogen. So if you're, let's say, producing hydrogen from methane using steam and some catalyst, you are essentially reforming it, and you are then going to also produce some CO2. Okay? This CO2 will have to be, if it is captured and stored, then the hydrogen thus produced is termed as blue. And then if you do steam reformation without carbon capture and storage, it is called as gray. And if you do pyrolysis of natural gas, it is termed as turquoise, because pyrolysis leads to liquid and solid wastes that are produced, and these can be much more easily separated, which is and then sequestered and stored. Okay. So instead of emitting the carbon dioxide into the atmosphere, or capturing it as carbon dioxide and then absorbing it into metal hydrates or whatever, you are essentially taking out the carbon in the natural gas in the form of solid or in the form of some oils, which can be easily stored. Then there is the coal gasification, which is termed as brown hydrogen. Coal gasification, again, of black coal is termed as black hydrogen. These are all extremely polluting technologies. And then you have the hydrogen that is already available underground, which is called as white hydrogen. There is, of course, as far as India is concerned, based on the National Green Hydrogen Mission, the biomass gasification, which produces hydrogen, is also termed as green hydrogen. This is because it has the potential to be a carbon neutral, or in some sense also a carbon negative technology, because you are, hello? Yeah. Was there a question? Sorry.
Yes, Suraj sir, can you please mute your mic? Sorry, sir.
Yeah, no problem. So, the biomass gasification that produces hydrogen, that technology has been termed or categorized as green hydrogen, because biomass, which is obtained from, let's say, organic life forms, mainly from agricultural waste and from various trees and plants, can be termed as renewable. If more trees are planted, or if you plant as many trees as the carbon dioxide released into the atmosphere, then it is in effect a carbon neutral technology, and so it can be considered to be green. That is the National Green Hydrogen Mission policy that has been implemented at the moment. So it is important to look at the Indian perspective also on this. So if you are working on, let's say, biomass gasification, you are contributing to the green hydrogen mission in a major manner. Right. So let's look at how hydrogen is produced. Where does the hydrogen that we use currently in our various technologies come from? Okay. The most common technique is steam methane reforming. Where the methane comes from, again, is a question. That methane could be from the natural gas fields underground, and it is a major fossil fuel, or it could be from other sources such as biogas, which is produced from biomass, which are agricultural waste, or human and animal waste, and so on. Okay. So as you can see, if you use hydrogen, if you produce hydrogen using various primary energy inputs such as electrical energy, it is called as electrolysis. If you input some thermal energy, there are various thermochemical processes that you can use. Many of these you also utilize some catalysts. There is the photonic energy, which is essentially what are called as photoelectrolysis. You have the energy obtained from the these are PV electrolysis, meaning the photovoltaic cell provides the energy for the electrolysis. And then there is the other one, which is photoelectrochemical, meaning the energy for the splitting itself is obtained from the light that is available from the sun. That catalyzes. There is an additional catalyst also, the energy is obtained from solar radiation, and the catalyst catalyzes the reaction. Then there's biochemical, which is termed as dark fermentation, which is just being seen in a major manner. The only limitation with this is that it is a very slow process. It takes a very long time to produce significant amounts of hydrogen. Then if you provide electrical and thermal energy inputs, you can carry out coal gasification, because coal gasification requires heating, and that can be either through thermal or through electrical, or a combination of both. And then you have fossil fuel reforming, like steam methane reforming, which also can be done through electrical and thermal means. Then there is electrical plus photonic and photonic plus biochemical. These are all various techniques, but the most common one, as I already mentioned, is steam methane reforming. Electrolysis is considered to be green, but it has the energy input has to be from renewable sources. It can be from a hydroelectric power plant, or it could be from wind energy, or from PV, solar PV energy, but it has to be renewable, and only then it is termed as green. And then gasification, this produces syngas, which is further processed in water gas shift reactor for producing more hydrogen. So if you look at the cost of production of hydrogen, if you think about the traditional method, which is the steam methane reforming, so from natural gas, which is methane, if you reform it using steam and catalyst, it costs close to 0.5 to $1 per kilogram. By today's rates, that would be about about, let's say, close to 45 to 85 rupees per kilogram. If you add some carbon capture and utilization and sequestration techniques, this will go up in cost, because these technologies also require energy input, which means that you are essentially you will have to provide more input energy than the amount of hydrogen that you are producing. So the cost goes up. That is about $1 to $2 per kilogram. And from electrolysis using renewable energy sources, this is extremely high. It's right now around $3 to $8 per kilogram. Again, depends on what is the primary energy source that you utilize. So some other numbers in perspective, if you want to produce 1 ton of hydrogen, you require 9,000 liters of water for the electrolysis, about 50 megawatt hour for the proton exchange membrane electrolyzers and alkaline electrolyzers. And if you want to use, if you want to carry out desalination of water and then use that water for electrolysis, then an additional 9 megawatt hour energy is or power is required. So the total requirement would be about 59 megawatt hour of electric power. And then you have, and 1 ton of hydrogen only generates 33.3 megawatt hour of electricity. So it is clear that the energy input of about 50 to 59 megawatt hour is not what you obtain from the hydrogen that you generate. But if you ask yourself this question, why do we then go for hydrogen? Okay. So one major reason is that, let's say you have continuous electric power supply at your home. Okay, of course, not counting the times when there is a power outage. But you usually get continuous power supply, and depending upon your load conditions, in the morning you are cooking, so you might require the use of a mixer, grinder, and maybe some additional equipment. And in the nights you might be using some air conditioners, fans, lights, in addition to what you would be using during the day. So in all of these cases, the variability has to be built into the grid, and the solution for actually storing electric power is by using electrochemical methods such as a battery. And although it is a relatively high energy density storage technique, you cannot store a lot of power in it or energy in it. And it's always better to store energy in the form of a fuel, because it is a very stable way of storage, meaning that whenever you require energy, you should be able to obtain it from the fuel directly. So the chemical storage of energy is the most stable way. batteries can discharge. You cannot expect a battery to work the same way after, let's say, 10 days. Okay? It would have discharged slightly, and that is why there is always a date that's mentioned on these batteries. It has to be seriously considered, because you cannot use a really old battery. They would have discharged almost completely. So the chemical storage is always sought, and whatever energy is available during the day in the form of, let's say, renewable sources such as solar radiation can be used to produce hydrogen by the electrolysis of water. This hydrogen is stored as a fuel. So the solar radiation, or the energy available in solar radiation, is now stored as a chemical energy in hydrogen as a fuel, and this is a stable storage. As long as the hydrogen does not leak, you have a good way of ensuring that the energy is not lost. Okay. So although the amount of energy that you input and the amount of energy that you can obtain are quite different, you still get a very stable storage technique. That is very important. So now, if you look at the electrolysis of water, this is a very promising method of hydrogen production. Anyone who who says that they are working on green hydrogen is probably exploring electrolysis of water as the solution. It is green if electric power is from renewable sources. This can be used outside of the grid, meaning that you do not have to depend on the grid for the electric power required to split water. There are three very common electrolyzers that are available. One is the proton exchange membrane electrolyzer, where there is a voltage that is applied across the electrolyzer. There are electrodes, and you have hydrogen ions crossing the polymer membrane. This forms the hydrogen at the cathode. The most common catalyst that is used is some platinum based catalyst. These are usually noble metal based catalysts. Okay. And the electron obviously flows in the external circuit. This is how you supply the electric current or apply the voltage. This is as far as the PEM electrolyzers are concerned. And then you have solid oxide electrolyzers. They use ceramic solid oxide as the electrolyte, and they operate at slightly elevated temperatures of about 700 to 800 degrees Celsius. Here, the oxygen ions actually cross through the electrolyte, and they move to the anode to form oxygen, and hydrogen is formed at the cathode. And steam is reduced at the cathode. High temperatures are involved, as I already mentioned. And alkaline electrolyzers are another category where the electrolyte is not a solid oxide or the polymer membrane. Here it is a alkali such as sodium or potassium hydroxide. So the schematic that is shown here is of a PEM electrolyzer. The other technique that I discussed is steam methane reforming. A hydrocarbon based fuel, most commonly natural gas, is used. You can actually use other heavier hydrocarbons also, but the amount of hydrogen that you will get per mole or per kilogram of the fuel would be lower, because methane has the highest carbon to hydrogen ratio in all hydrocarbons. It has 4 hydrogen to every carbon atom. Okay. For instance, even if you take the higher alkane, which is ethane, you have C2H6. So the hydrogen to carbon ratio there is 3/1. Okay. So it is methane which is most advantageous, because it can produce maximum hydrogen for every mole of natural gas. So some high temperatures are involved, about 800 to 1000 degrees Celsius, and high pressures in the presence of a steam and a catalyst. If you do not use a catalyst, for instance, then these temperatures will be much higher. So you initially produce hydrogen, carbon monoxide, CO2, some residual methane, and water is also produced. Essentially, the reforming process is a partial oxidation based process, which partially oxidizes rather preferentially oxidizes carbon in methane as opposed to hydrogen. And if there is still some water that has been produced, as you can see here, this is sent to the water gas shift reactor, which contains some additional catalyst that will further reduce the water to hydrogen, and again oxidize the remaining carbon monoxide to carbon dioxide. If you incorporate CO2 capture, then this makes the technique greener, but you are still using a fossil fuel based resource, which is natural gas, and so maybe it is not the most ideal of solutions. So if you, for instance, use biogas, which mainly consists of about 40 to 60% methane, for reforming, you can produce hydrogen, and if you capture the CO2 there, then it can be termed as green hydrogen, because the biogas is produced from biomass, which is anyways going to waste, and you are also capturing the CO2 that is thus being produced. So it is a win-win situation. So methanation is always also involved sometimes to remove the additional CO and CO2. This meaning that essentially the CO2 and CO and CO2 can be converted to methane also. Sometimes we use some methanation processes also. It will require some catalyst to be used. So the other technique is, as I already discussed, biomass-based hydrogen production. This can be termed as green primarily because if you are using sources that are basically agricultural based, or you are planting trees for the purpose of producing hydrogen from biomass. Okay. So there are various techniques. There is the thermochemical technique, which is most common. You have a gasifier, doesn't use any catalyst, and it can produce CO and H2, and you can do further steam reforming, partial oxidation, and other reforming processes to produce more hydrogen and CO2. There is also the pyrolysis process, which is very important. It can be used with carbon capture and sequestration techniques. But this requires catalysts. Otherwise, the temperatures and pressures involved are relatively higher. Then there is the microbial electrolysis. This is not a very major process, but it is still being used. Then there are the biological processes. There are anaerobic processes which produces biogas, majorly methane and carbon dioxide, which can be further sent to a water gas shift reactor to produce hydrogen and carbon dioxide, or to steam reforming and so on. Then there is the alcoholic this thing, which is essentially what is used in the sugar industry. It can produce ethanol. Ethanol can again be reformed to produce CO2 and H2. Okay, so reformation is essentially a process where you do preferential or partial oxidation and water gas shift reactions to produce hydrogen as a fuel. And transesterification is also one more process where from biomass you can produce biodiesel, which is essentially from vegetable oils. Vegetable oils meaning oils that are obtained from plant sources. These oils are transesterified to produce biodiesel. This biodiesel again is a hydrocarbon source that can be reformed to produce CO2 or H2. And then there is the glycerol that is also produced in the transesterification process, which can again be used as a fuel for reform. So when you take the hydrogen that is produced by these techniques, electrolysis, steam methane reforming, or through biomass based processes, where is all of this hydrogen be going? On the left hand side, you can see what are the production techniques. Let's say you are doing steam methane reforming of natural gas, or let's say you're doing coal gasification, or it could be from oil or from electricity, meaning the hydrogen produced by electrolysis, or there can be some byproduct hydrogen also. For instance, the chloralkali process, which many fertilizer industries carry out, produces hydrogen, and this is what is called as byproduct hydrogen. And if all of these are looked at as to where they are going, you will see that a significant amount of it is going to is being lost. It is not utilized, and a lot of it is going for refining or in ammonia production or in transport or methanol. DRI is direct reduction of iron. I'll talk about it a little later. And then there is also heating and furnace applications, which where the end use is direct heat production and so on. So for refining, for ammonia and for transport and other applications, you require pure hydrogen. And for some other applications, it's hydrogen that is mixed with other gases that is essential. So it is not really a major concern if the hydrogen is slightly pure also. So one of the major utilities of hydrogen is for producing grid power. It takes us towards the renewable energy power production. What do you say? Primarily because during the day, as I mentioned, you can rely on the solar PV based power production techniques, and you can directly supply it through the grid. Although that is not being done. Solar power or solar PV based power is still being used only for captive energy production. It is usually not incorporated into the grid. Okay? It can be used to support the grid, but it is not used to run the grid itself, because there are significant losses in this thing, and it can never really operate a complete grid on its own, because the energy requirement is extremely huge. On the other hand, for supporting the grid, you can also use hydrogen. This requires energy and fuel storage infrastructure, because you are producing hydrogen during the day, you are storing it, and you are utilizing it in the time when, let's say, solar power or wind energy or hydroelectric power is not available. Large capacity installation are now being planned using the pure hydrogen. One such pilot plant is the 400 megawatt capacity natural gas co-firing hydrogen plant that is established in Takasago Hydrogen Park at Japan. This utilizes up to 50% of co-firing with hydrogen. So 50% is natural gas and 50% is hydrogen, and the capacity is about 400 megawatt. So these can be scaled up, but again, it must be stressed here that hydrogen requires very significant infrastructure in terms of storage, not just for the fuel, but also for the energy that is being produced. So hydrogen supply is usually the bottleneck, because you will need to produce hydrogen at a rate which can be utilized in such power plants. And the other concern is that because these use conventional techniques for power production using hydrogen, meaning that it is combusted in a gas turbine engine, which is liable to produce a lot of oxides of nitrogen. The hydrogen flames are usually of higher temperature. This can lead to the dissociation of nitrogen, and this nitrogen can then react with oxygen in air and produce oxides of nitrogen, which are a significant cause of environmental pollution. These are not greenhouse gases, but these can cause a lot of damage to the environment through acid rains and so on. So gas turbines can be operated with hydrogen. We are now starting to look at fuel flexible gas turbines, namely hydrogen and using hydrogen and hydrogen carriers. Ammonia is one such fuel, because ammonia can be stored as liquid at slightly higher pressures. At room temperature and pressure, it is a gas, but at slightly higher pressures, it can be stored as a liquid at room temperature, which is an advantage, because this takes away the problem of storage of hydrogen as a fuel. Now, ammonia, which is a hydrogen carrier, is a very stable compound, although it is very toxic, and it is also can cause significant health issues. I'm sorry, am I still connected?
Yes, sir. Yes.
Yes,
Yeah.
correct.
Yeah. Right. Right now, we are blending hydrogen with natural gas and using it. There is the issue of high NOx emissions if you use it in conventional gas turbine engines. So it is important to mitigate such effects. And there are other synthetic fuels that use, that carry hydrogen but do not carry what do you say, carbon. Okay? Because the combustion of any carbon based fuel will produce carbon dioxide, which is not desirable. Okay? And of course, NOx is also not desirable because there are very stringent norms as far as NOx emissions are concerned. So this schematic shows a gas turbine engine which uses a blend of natural gas and hydrogen, and this shows a kind of integrated system where solar PV panels are used, electric power is produced, you have an electrolyzer unit that produces hydrogen, and the hydrogen can be used in a combustor, and you can run a low pressure turbine or a high pressure turbine. Some of the energy input is used to run a gasifier, where biomass is used to reformed to produce carbon monoxide and hydrogen, and that is used in a combustion chamber to run the turbine. So such technologies are being looked at. So it can be if you look at the solution for grid power, I talked about gas turbine engines which co-fire both natural gas and hydrogen. But if you look at off-grid power production, the solution is to use a fuel cell. Okay? Fuel cells are very small energy producing devices which can be used for smaller power applications. These are not meant for supporting the grid, but much more to do with, let's say, powering a single house, or it could be for mobility applications. It can be used for powering a small car, or nowadays the demonstration or pilot projects are being carried out on mobility of trucks also using hydrogen fuel cells. So it can be for domestic or industrial power requirements, but at a smaller scale. Fuel cell stacks are used. So using renewable energy sources, you you operate an electrolyzer which splits water to hydrogen and oxygen. The hydrogen is stored, and then it is used for producing power during off-grid operation in the fuel cell, and this is sent to the storage, and as and when the energy is required, it is supplied. And then there is also the backup generator which is incorporated into this system. So the capacity is typically of a few megawatt. It is not of the order that we've seen as far as grid applications are concerned. The maximum demonstrated capacity is around 75 megawatt in South Korea. But the cost of production is very, very high. That's something that you have to really worry about. Fuel cells use, again, catalysts which are based on noble metals, and they are extremely expensive. And currently, fuel cell efficiencies are still relatively low, and people are working on improving the efficiencies by a significant extent. Power converters for electrolyzers and fuel cells are required because they they need to be modular, and they will have to incorporate the variation in the input power, because wind energy is unpredictable. PV arrays also do not produce stable power. Even during the day, it can peak at noon and then again taper off during the evening and in the morning. So those kinds of variations will have to be accounted for using some power converters, and so that it's a stable supply also. So fuel cell is essentially an electrochemical cell which uses hydrogen as a fuel with the oxidizer as air, and you produce electron flow in the external circuit, which is the electric power which can be used to operate various electrical equipment. So there are applications in automotive transport as well, but it is also seen as a major source for domestic and industrial requirements, primarily because hydrogen uh, cannot be stored easily for mobility applications. So if you want mobility applications, you will have to have large tanks for hydrogen storage, which is much more easier for stationary power generation rather than for automotive applications. The maximum efficiencies of typical fuel cells is around 60 to 70%. There are three kinds again, like electrolyzers: the proton external membrane electrolyzer, alkaline and solid oxide fuel cells. Remember that a fuel cell is quite literally the reverse of an electrolyzer, but of course the efficiencies are not the same when you operate it as an electrolyzer and as a fuel cell. There are a couple of other types of fuel cells, namely the molten carbonate and phosphoric acid fuel cells, and ammonia and methanol are also candidates that can be used as fuels instead of hydrogen, which makes it very promising, because then you don't need to worry about storing hydrogen. Ammonia and methanol are much more easily stored. So there is significant research potential as far as fuel cells are concerned, because the catalytic material used for electrodes, for coating the electrodes, is an active area of research. You can look at reducing the precious metal loading, extending the surface. You can try and have extended surfaces on the electrodes for maximum durability and increasing the activity of the catalyst. There are studies on various electrolytes of alkaline fuel cells, because they do not use precious metal catalysts on their electrodes. For solid oxide fuel cells, there is still very active work on what kind of electrolytes can be used, which are effective at lower temperatures. Also, we want to look at low fuel purity based operation. Right now, PEM fuel cells cannot tolerate any contamination in the hydrogen that is supplied, but solid oxide fuel cells can tolerate even up to 10 to 20% of, let's say, carbon based compounds like carbon dioxide or carbon monoxide. So stack performance is also very important. The kind of performance you will get from a single cell of a fuel cell, or for that matter an electrolyzer, is not the same as what you would obtain from a stack. And there is also a lot of work that is being carried out on the thermal management of cells and stacks, because they can get heated up quite frequently, and that leads to degradation of the material and also reduction in the performance. So for transportation applications of hydrogen, there are various applications that can be seen at. One is for surface transportation, namely trains or cars and trucks that are operated. Then there is marine and air. Fuel cells will be prime movers for surface transportation, road and rail applications, because they require much lesser power outputs. But currently we are using IC engines as the major source, because it is proven technology. So there are hydrogen IC engines that have been developed by Ashok Leyland. Toyota has some technology. Cummins has technology for hydrogen to be fired or to be used as a fuel in IC engines. But fuel cells are catching up. The advantage of using a fuel cell as opposed to IC engine is that the NOx emissions can be avoided in a fuel cell. But you could think of it as a low-hanging fruit to use IC engines. Still, fuel cells reach a point where their efficiency is significantly higher. Because if you want to immediately replace fuels in or to incorporate hydrogen majorly in mobility applications, then hydrogen IC engines is the way to go, because fuel cells are still not a very advanced technology. It is a nascent technology. Then you have marine applications. Fuel cells are being used for short range, and IC engines for long range applications. In fact, there are ferries in Kochi Metro which are being used for operating which are being operated using hydrogen fuel cells. Then there is the existing technology is the replacement of existing technology is a major deterrent. People are little rigid to move to the new technology of fuel cells. And the storage is also a major concern as far as transportation is concerned. I mean, or for transportation applications, because you will need very high pressures, and even then you will be able to store only very low amounts of hydrogen. So here there are various possibilities. There is the onboard hydrogen storage that is to be seen. Stationary storage is usually not a concern because you can have large capacities on terrestrial applications, but not for mobility. Fuel cell efficiencies need to be improved. Again, there the catalyst material and various other alternate catalysts are also being looked at. IC engines are proven technologies, but we need to worry about the emissions, NOx emissions majorly. And then there are various novel fuels that are being produced from hydrogen, namely the sustainable aviation fuel that is being seen majorly for aircrafts. Ammonia can be considered, methanol for marine engines, methanol for long haul trucks has already been demonstrated. I think Ashok Leyland has methanol engine which they have demonstrated on some buses and trucks in Bangalore. In Kerala, Kochi metro feeder buses, Kochi International Airport buses are planned as fuel cell powered technologies. Coming to refineries, hydrogen is used for hydrodesulfurization operations. Whatever is obtained from the steam methane reforming inside the refinery itself. So if you go to again the Kochi BPCL refinery, they produce hydrogen in a major way, but much of the hydrogen that they produce is also used in their own facilities for the processing of crude oil, because it is used in hydrodesulfurization process. The process is essentially removal of sulfur removal using catalysts such as molybdenum and cobalt. And then it is the most important sulfur production process. Produces about 64 million metric ton of sulfur using this hydrodesulfurization in refineries. As I mentioned, hydrogen being used in refineries is one of the major end users of hydrogen, whatever way it is produced, and it consumes about 2.5 million metric ton per annum in India alone, and this is the second largest application for hydrogen. So these are the various other processes where hydrogen is used in a refinery: hydrocracking, hydrotreating, hydrogenation, and hydroisomerization. As the name suggests, all of these processes require hydrogen as a raw material. The other application for hydrogen is chemical industries. You can utilize hydrogen in a significant manner there. It can be for production of ammonia. Again, I'm not talking about the fertilizer alone. This is for ammonia as a raw material for some other chemical products as well. For hydrochloric acid production, hydrogen is required, methanol production, hydrogen peroxide production, and so on. And ammonia is majorly used for fertilizers and also for certain other applications. So this schematic shows the various pathways by which different products can be produced from hydrogen. For instance, hydrogen along with nitrogen produces ammonia. The process is called as Haber-Bosch process. It's a age-old process. It's energy intensive, and it is very important in the fertilizer industry. Amines can be produced, then cycloalkanes, hydrogen peroxide, saturated compounds, derivatives of alkanes, alcohols, and then through various means. So this is as far as the chemical industries is concerned. Fertilizers, ammonia is produced through the Haber-Bosch process. It is used as a precursor for urea ammonium nitrate, ammonium phosphate, and other fertilizers that are very commonly used. And this is the largest use of hydrogen after, this is the first one, and then the second is the refinery application. So if you want to use hydrogen as an alternative in any other industry, you will still have to keep in mind that the requirements of the fertilizer industry, or for that matter, the refining industry, cannot be overlooked. So any hydrogen that is going to be used will be in addition to these the requirements of these industries, namely the fertilizer and refineries. So ammonia is in some sense one chemical which has many applications, which could potentially have many applications. It is a liquid at relatively low temperatures and low storage pressures. Marine engines can be operated with ammonia. There have been some pilot studies that have been carried out. It is a stable energy storage material as a fuel. Chemicals can be produced from it, namely fertilizers and some other chemicals also. It is, on the other hand, it is a very poor fuel with low flammability. We can design gas turbine engines with ammonia as a fuel, and because the temperatures are relatively lower, and it can be also used in the fertilizer industry in the major part. Some other applications is production of synthetic fuels from hydrogen, namely methanol, sustainable aviation fuel, higher alkanes, which are substitutes for petrol or diesel, can be produced. Some alkenes can also be produced. These can be used in marine engines and long haul trucks. A very small application for hydrogen is the process heat for domestic applications. Namely, let's say you want to blend it with natural gas and use it for cooking applications, or it could be for domestic heating, especially in Western countries or in very cold climates, or in industries for operating furnaces. Because hydrogen has a very high heating value, it is about 3 to 4 times of conventional fuels. Process heat boilers can be used. They will only require about 1/3 of the hydrogen as opposed to the conventional fuel. The flame temperatures are very high, so you will need to worry about NOx emissions. And co-firing with other conventional fuels is one option that can be looked at. Coming to steel industry, this is a very common application for fossil fuels, where hydrogen can make a mark. So in a steel industry, where iron extraction from iron ore is carried out, iron ore is then is made into pellets, and then you have the fossil fuel that is introduced through what are called as tuyeres. This leads to a very high temperature inside the blast furnace, where additional coke is added. Coke is used as a reducing agent. There are various reactions that take place. CO plus O2 going to CO2 is the reaction that produces high energy by the combustion of pulverized coal. And this CO2 reacts with carbon in the coke, producing carbon monoxide. And the carbon monoxide is then used to reduce iron ore, which is Fe2O3 majorly, to iron and carbon dioxide. So essentially, you have a lot of carbon dioxide that is being emitted by the combustion, and also by the reduction of iron oxide. So this is the process that is being followed. The approach involves a lot of fossil fuel in the form of pulverized coal and in the form of coke. The approach that could be followed is what is called as green steel, which is essentially the iron ore is pelletized using hydrogen or renewable energy powered mills, and then you can, instead of reducing the iron ore using carbon monoxide, which is produced from the partial combustion or the from coke and pulverized coal, it can be directly reduced using hydrogen itself. Hydrogen gets oxidized and Fe2O3 is reduced. Okay. So this is called as direct reduction of iron using hydrogen, and this is being looked at in a major manner as far as steel industry is concerned. So this has huge potential. As you can see, China uses about, produces about 1,033 million ton of steel annually. Globally, it is about 1,951 million ton. and out of this, China alone produces close to 70% this thing, and other countries do not have much potential. So if the fossil fuel utilization in the production of steel can be replaced by green hydrogen, then it can significantly reduce the emissions. So there are other uses. I will not go into this. It can be used even in pharmaceutical industries, glass industries, in the production of float glass. It is used in food industry for hydrogenation of oils, which is usually not a very good thing, because hydrogenated fat is not very good. It's essentially what is called as saturated fat. It has detrimental health effects, but it also improves the storage and shelf life. So what you know as vanaspati or dalda. Dalda is of course a trade name, but vanaspati or hydrogenated fat is essentially detrimental to health, but it can be it can be stored for much longer. Oil or let's say ghee will not stay for long, but hydrogenated oils can stay for much longer. That is why margarine or butter spread that you get, which is hydrogenated, has a much more longer shelf life. So to try and conclude this, if you look at the global perspective, hydrogen economy is booming. It is of course very important to reduce fossil fuel dependence and carbon-based emission. Currently, in the near past, the hydrogen demand was only around 95 million ton in 2021, and it contributes to only 2.5% of the energy demand of the whole world. And this is not just for power production, but also as direct utilization in, let's say, refineries or in other applications. So now there is a major increase in industrial and refinery applications, and so it is important to increase the capacities. Currently, we have not improved the green hydrogen production capacity, and it is still less than 1 million ton. Okay, as opposed to the 95 million ton that is required, only less than 1 million ton is produced from green hydrogen, or is green hydrogen, meaning that about 94 million ton or more is being produced by steam methane reforming, which is not green hydrogen as such. So the projected capacity in by 2030 is about 16 to 24 million ton through electrolysis, and 7 to 10 million ton from the SMR routes with carbon capture and sequestration techniques, meaning that these can be termed as green hydrogen pathways, and you could go up to around 35 million ton out of the 95 million ton, which of course will also go up. So if you consider that as about 100 million ton in 2030, you will be producing close to 35 million ton through green routes. What about India? So we have by 2050, the demand for hydrogen is expected to increase by 400%. We are developing green hydrogen production capacities of at least 5 million metric ton per annum, with an associated renewable energy capacity addition of about 125 gigawatt. So essentially what we are trying to do is we are adding to the renewable energy capacity of this much, so that we can operate green hydrogen plants, mainly run through electrolysis techniques. And this would lead to about 5 million metric ton per annum of hydrogen being produced. And for this, about 8 lakh crore is required in total investments. There is a scope for about 6 lakh jobs. The cumulative reduction in fossil fuel imports can be up to 1 lakh crore. And we can reduce the annual greenhouse gas emissions by as much as 15 million metric ton. Okay. Right now, although I had converted the US dollars to rupees and mentioned it, here you can see the actual levelized cost that is for production of 1 kilogram of hydrogen is about 400 rupees at present, and this has to be brought down. And the challenges in the hydrogen economy are mainly infrastructure, because hydrogen distribution networks are still in development. For that, the government of India has introduced through the Department of Science and Technology what are called as Hydrogen Valley Innovation Clusters. One such cluster is going to be established in Kochi with ANERT as the nodal agency for the implementation. So these innovation clusters will mainly focus on the end-to-end hydrogen infrastructure or the value chain, starting from hydrogen production, green hydrogen production specifically, storage, distribution, and offtake. So you can produce hydrogen from renewable energy sources, and then it will be stored, it will be distributed to various end users, and the end users, namely fertilizers and other mobility applications, are all going to be explored. So various industry partners are involved in this. R&D partners are also taking up projects to make this much more efficient and to add to the production capacity and to scale it up in a major manner. So currently production costs are very high. The extraction of hydrogen from whatever sources contain hydrogen, namely water, is still a major challenge. Okay. Transporting hydrogen is a very major issue at the present. Political and economic interest, this is what in the West is called as lobbying, because energy companies or oil companies will lobby against hydrogen as a fuel, saying that it is very difficult to store, it is not a good fuel, it can explode, and so on and so forth. There is also a media bias against hydrogen, again due to the fact that it is very difficult to store and things like that. And the government support is very important to promote the utilization of hydrogen in a major way. So what is the way forward? It is important to improve the efficiency and the processes in industries significantly. Electrolysis is a major contributor, and but one must not ignore other processes like biomass gasification and so on. Biofuels can reduce carbon emissions while still using the existing technologies, namely combustion of various fuels. Just that now the source is biomass, which can be termed as renewable, because you are again going to fix the carbon that is emitted to the environment. So we should first target net zero and then move to carbon neutral technologies. Synthetic fuels can be majorly looked at, because they have applications for hydrogen in transportation and power sector. Policy and incentives from the government are also important, and it is important to leverage existing technology while also developing new technology. So I'll leave you with this question. Is hydrogen the savior? Currently, it doesn't. It's something that we are not very sure about, primarily because, as I already mentioned, the amount of energy that you have to input to produce hydrogen is much higher than the energy that you are going to get from hydrogen as a source of energy. But it is important from the perspective of mitigating greenhouse gas emissions, and so we must continue to explore hydrogen and try to optimize technologies for hydrogen as the fuel for the future. So thank you, and I'm open to questions now.
If anyone have any questions.
Good evening, sir. Sir, actually, this green hydrogen production, it is a water-intensive process, right? So
yes,
it will pose a challenge on the water resources, which is still challenging the sustainability. So what about the possibility of hydrogen production from seawater?
Okay, so the existing technology cannot operate with seawater or brackish water, saline water. None of these can be directly used in conventional electrolyzers. It may be PEM or solid oxide or whatever. There are certain other processes which can be used. For instance, the chloralkali process. It in fact takes water, and the current process in the industry for chloralkali is where hydrogen comes out as a byproduct. There, water is NaCl is added to water. Essentially, salt is added to water, and you produce NaCl, and that is the name chloralkali. Okay, and you produce hydrogen from that, and also sodium hydroxide. So the point I'm trying to make here is that it is no electrolyzer currently can operate with seawater or salt water, but the existing technology uses desalination as a means of obtaining pure water to produce hydrogen. Okay, and that is where as I had indicated, you require some additional power input of about 9 megawatt hour to produce pure water from seawater or salt water. So that is a problem which can be only mitigated by, as you mentioned, electrolysis of seawater directly. But it might not also be very easy to do it, because you're essentially you'll make the process less efficient perhaps, and it might also not give you very what do you say, the energy input would still be pretty high. Okay, so yes, as you mentioned, in terms of sustainability, it is not a very good idea at all. But what you must also appreciate is that let's say you have electrolysis of whatever water source you have. You're going to do that, and whatever hydrogen and air you are, oxygen you are producing, that goes back into the fuel cell, and you are going to produce hydrogen. Water again. Okay, even if you don't put it in a fuel cell, if you put it in an IC engine, for instance, there also the product is water, which will go back into the atmosphere. It will move to the clouds. It is going to come back as water to the earth. So any water that you use, okay, we keep talking about water wastage and so on. Water that we use for any application on the earth is not leaving the earth. It will come back to the earth. It is just not going to be in the same place as where it is replaced. That's all. Okay. But in terms of sustainability, I totally agree. Yes, it is not a very sustainable practice. Yeah.
Thank you, sir. It was a very informative session. You have clearly explained all the aspects of hydrogen.
Thank you. Thank you.
So, if anyone have any doubt?
Good evening, sir. Very good
Yes.
evening, sir. Very nice session, sir. Thank you so much, sir.
Thank you. Thank you.
So your speech was not only riveting, it left a lasting impressions on all of our attendees. And this program is meant to inspire people to take actions. So your speech helped wake people up to that topic, providing new context and details about green hydrogen, global hydrogen, hydrogen productions, and layout of future gas turbines, and etc. So this session was very informative, and
Yes.
as we come to the end of today's program, on behalf of everyone's here, we would once again like to thank our esteemed guests for their invaluable contributions and gracing us with their esteemed presence today. And as we will cherish your words of wisdom and look forward to applying them in our personal and professional lives. So thank you for adding immense value to our gathering today. And as we close this event, let's heartily applaud our honored guest. And thank you everyone for joining us in showing your appreciations and gratitude. Until we meet tomorrow at 6 p.m. for the next sessions. Have a beautiful evening, each one of you.
Thank you.
Thank you,
Good
sir.
night, everyone.
Thank you. Good night, sir.